Thanks a lot. It's great fun to be back here. So I'm going to talk about parallel repetition. Parallel repetition is a fundamental operation in theoretical computer science and complexity theory. As some of you know, so it's this very weird theorem. It's a very easy formulation, kind of a difficult proof and weird parameters. And this talk is about how to get a really simple proof and get ideal parameters. Let's do it. Okay, so let me first tell you what this theorem is all about. So parallel repetition is an operation. It's a theorem about two prover games. And the games that I'm going to care about are games that are called closed versus closed games. So what's that? You're given a bunch of constraints and over some set of variables. And each constraint depends on some number of variables. And so you devise this two-prover game. A two-prover game is, there is a verifier, and there are two provers, and the provers decide ahead of time on some joint strategy, but then they're put into different rooms, and each gets some challenge from the verifier. The two challenges are correlated. They have to answer their challenge, their question, without knowing what's the question to the other guy. And what the verifier gets to do is to compare them against each other. Okay. So
trying to convince the verifier that this is satisfied.
Yeah. So the closed versus closed game wants to convince the verifier wants to check whether those C1 to Cm are satisfiable. The players, if it's satisfiable, they are sent to agree on some global assignment to the variables, and then the verifier starts asking them questions that they should be able to answer if everything is indeed satisfiable. Okay. So what do they do? Well, the verifier picks a random variable, uniformly at random, picks two random clauses independently that talk about this variable, and sends one clause to the first player, the other clause to the second player. And well, if everything is satisfiable, in particular, the two provers should be able, they're supposed to agree on assignment. The assignment should be satisfying those two clauses. So each one is supposed to send a satisfying assignment to the clause they got. Each clause depends on the variable, so it's assignments to the variables in the clause that are supposed to satisfy the clause. And then the verifier checks the two provers agree on the assignment to V. Okay, and the important definition is what's the value of the game. And the value of the game is suppose that the provers decided ahead of time on the best strategy they have, what's the probability that the verifier accepts. Okay. This is the example. Right, like 3-SAT, right? You have a 3-SAT formula.
3-SAT is?
Right, so there is, okay. So there is this canonical NP-hard problem, right? So the canonical NP-hard problem is you're given like a 3CNF formula. So it's a formula like that, and here there are variables or negations of variables. And you want to check whether it's satisfiable. So this will be your constraints. And if you do this game, then the value of this game is 1 if and only if this formula is satisfiable. Okay, so this proves that computing the value of the game is NP-hard, right? This is the canonical NP-complete problem.
Let me give you a different example that you may know. If you have coloring problem, so three coloring of the graph, the constraints are well behaved that the two colors are different. Yeah. So in this game, these two guys want to convince the verifier that there is a three coloring to the graph by picking a vertex and picking two edges on it and asking the two different provers to provide coloring of the endpoints of the edges. But the only thing he's checking is that they are different, so they are legal assignments just to these edges, and that they agree on the color they give to the control.
Right, and the value is 1 if and only if there is a coloring of the vertices that exactly for every edge you have two different colors.
If there is a rigorous recurring, of course they can just agree on one.
They know everything. They're infinitely powerful. And the verifier is this polynomial time verifier that tries to check them. Okay? There is no strategy.
There cannot be one.
Okay? Right, so this is what we usually do. We set up those two-prover games for NP complete problems. And it's usually easy to obtain that the value is 1 if and only if there is a solution that satisfies everything. And value is, yeah.
What's the advantage of having two provers?
It's a very useful conceptual device. So the advantage is that then, right, you can say the same thing in two different ways. You can say that there is one player, but then it first completely commits to the coloring, and then we check him at a random place. This way, they don't have to commit to a coloring ahead of time, right? They can just answer a challenge, but the thing is that they don't know what's the challenge of the other guy, so we still are able to do things as if they actually committed to a coloring.
The standard example is that you have, like, the police put suspects in two different rooms, and they don't have the fact that it's the other suspect. That makes it harder for them to watch.
Okay. Any other questions about two-prover games? That's like the main, the basic concept here. Okay. So this is two-prover game. This is like even a game of a special form. It's what's called a projection game, right? So you have the constraints, and the assignments to the constraints give assignments to the variables, right? It's the same thing with coloring and other things. And these are this is an incredibly important family of two-prover games. This is, you know, the basis of all hardness of approximation, and these are the games that we're going to care about in this talk. Okay, good. So these are two-prover games, and there is this very famous PCP theorem that says that for any NP problem, you can actually devise such a game. And not only that the value is going to be 1 if and only if the answer is yes, but actually you have a gap, right? If the answer, if the formula is satisfiable, then the value is exactly 1. If the formula is not satisfiable, then the value is going to be bounded away from 1, maybe 0.999. Okay? This is this it's a big theorem, and it's a very important theorem. It's very unclear, right? If you just think of how do you do that for coloring, right? It's very unclear how you can obtain suddenly a gap. So I want to consider what the form that I specified in the beginning, the two clauses. Just you choose a variable, and then you choose two random clauses that could contain it. Okay? And this is the important class of. Yeah. Mm-hmm. Right. So this is this important probabilistically checkable proofs theorem. But the thing is, if you try to, it's not as easy. It's not a very strong theorem, right? Because the gap is very small between 1 and 0.99. And what would you really need if you want to do hardness of approximation or other things? You really want to replace this 0.999 with 0.0001. Okay, and this is where pair repetition comes into play. Because, right, so we have here some randomized procedure, and kind of we all know this trick that if you want to get better like error probability, well, you should just repeat what you have like k times instead of just 1 time. So what you can do is take the verifier, instead of just picking one variable and two constraints that contain it, pick k variables infinitely at random. For each, pick two clauses that two constraints that contain it, and do the game sequentially. And then if the provers keep continuing, then instead of 0.999, you get 0.99 to the k, right? And then if k becomes large, it becomes small, right? So this is standard, randomized algorithms. The trouble with this is that then you don't get one round game. You get a game with k rounds, right? You do it one time with one pair of clauses, and then another time with another pair of clauses, and so on and so on. Okay. And parallel repetition is the version of that keeps it one round, right? So the idea, so we will denote the new game by g to the k. If the original game is g, with k times. The verifier doesn't pick just one variable, it picks k variables independently at random. For each, picks two constraints that contain it, sends one set of constraints to the first prover, one set of constraints to the second prover, gets answers per clause, and checks each and every one of the k-tests. Okay? And the easy direction is that the value of this game is at least the value of g to the k. And the reason is that if the provers have a strategy that achieves value g acceptance probability, then they can just follow this strategy for each one of the k trials and obtain exactly, probability of acceptance is exactly value of g to the k. And the difficult question is the other side. Is it true that the value of g to the k is at most the value of g to the k? Okay. And notice that this is unclear because if you do this k-round version of this thing, then you really, right, they have some strategy in every round, the global strategy, and they always answer about it. Here, they get all of the questions ahead of time, and somehow their answers can depend on all of the questions, and they can do weird things, and we'll see an example in a few minutes. Okay, so this is the per repetition question. Do you have that? Or is it a decrease at all? And the answer to this question is that this is false. This is not true. And there has been like 25 years of research on this problem, and these are just like the highlights of this research. So this was a problem that was posed by Fortner, Rumpel, and Sipser around 1990. Was like this big open problem. Ran actually solved the problem in 94. He showed that the value does decrease exponentially. So if the value is 1 minus epsilon, the value after repetitions, it does decrease as something that is related to the value to the k with some other parameters there. The decay in the acceptance probability of the verifier is extremely weird. Yeah, some of it is actually inherent. Some of it is just an artifact of the proof. Notice that this is really a very weak, very slow exponential decay, right? Which, if the value is very close to 1, you maybe expect that the decay is going to be small. If the value is actually small, you still get the decay goes with like something very close to 1 instead of with the value. But this is like the celebrated Parallel Repetition Theorem. There was a lot of research on improving it and on tightening everything and getting simpler proofs. So this is one thing to highlight. The other thing to highlight is that actually right from the beginning there was this interesting idea that if all we care about is getting two-prover games that with low value, then we don't have to just take our game and repeat it. We can tweak the game a little bit and then repeat it, and then maybe it becomes an easier problem. This was an idea of Feige and Kilian, but they were only able to prove a very weak decay. The value decreases as about 1 over k. Avi, Russell, and Valentin actually kind of rediscovered this idea. Actually, when I was around the time that I was a postdoc here, and they were able to show that there is a better decay, but it was still exponential in square root k, which is weaker, much weaker than what Ran was able to prove, without tweaking the game. Okay, so this is like the brief history of per repetition. So yeah, let me just say that what I do in this work is I go back to this idea of let's tweak the game before we repeat it, and I actually get the right the ideal parameters. The value of g to the k is approximately bounded by value of g to the k, which this is the best it can be, right? Which is sort of feels right if you have the ability to tweak. You should get better results than if you didn't have the ability to tweak. But I think it's also the first time that you can actually really get ideal parameters. Okay. So this is the result. Let me tell you what I'm going to do in this talk. The first thing I want to do is explain kind of what's the problem with pair repetition. Why it needed all those 25-year long history. Why is it difficult? Why it doesn't behave kind of just like sequential repetition? So I'll show you an example, and we are going to look at this example and dissect it and understand exactly what's going on. And then I'm going to tell you exactly what are the parameters that I get and what I do. And then I'm actually going to show you the proof. For those of you who know the paper, I'm going to show you a proof that is even much simpler than what's in the paper. It's really like a 5-line proof. And it's a proof that anyone can understand. It only requires the definition of an extractor. Just plain old, right? Nothing complicated beyond that. Okay. So the first thing is what's the deal with pair repetition? Why it's a difficult problem? Let's see an example, and let's see that pair repetition behaves in a very counterintuitive way. So I'm going to define a special game. And the special game is Feige's non-interactive agreement game. And for the game, let's give names to the two players, Wang and Meng. And the game is as follows. The verifier is going to pick two random independent bits. Okay, so this is not like what we had before. It's usually the two questions to the provers are going to be correlated, right? This is this very stupid game where you have completely independent questions to the two provers. So say it picked 0 and 1, and it sends those bits to the provers. And then each player should say two things. It should give the name of a player, and it should give the bit. And when a player gives this pair of player and a bit, it basically declares, I think that player this got bit that. Okay, so Wang can say, Wang and 0, and Meng can say Wang and 0, and this means I declare that Wang got 0, and the other guy says the same thing. And this is what they should do. They should agree on a player and agree on the bit that this player got. Okay, so that's the game. Any questions about what's the game? Because I'm going to spend a few minutes talking about this game. Okay, let's think what's the value of this thing. So each player knows exactly what's the bit that player got. Okay, so Wang can always say Wang and the right bit because, fine. But the other guy knows nothing about the bit of the other player. And the way this is set up, basically, the best thing that they should do is decide on one player and always answer about this one player. So basically, the second guy can only guess. Right? So this is the intuition, and you can formalize it. And the value of this game is exactly half. One player knows, and the other guesses.
In general, they can always coordinate.
Yeah.
They can always coordinate before, yes. But then once they're put in different rooms, and then they get the questions, and they don't know. This is the same. And then the question is, what's the value of this game if you repeat it twice? And you would think that this is a quarter, right? And I'm going to show you something amazing. The magic is that the value remains half. Okay, even though we did 2 repetitions. So let me describe to you the strategy. What they're going to decide, so let's say first what's the game. So now instead of picking just one bit for this guy, the other bit for this guy, we pick 2, right? 2 independent bits for this guy, 2 independent bits for that guy. And they should give 2 answers. One is a player and a bit, and another is a player of a bit. One refers to the first round, and the other refers to the second round. Okay. So what's their strategy? They're going to decide ahead of time that they always answer about Wang the first round and always answer about Meng the second time. Okay. Now Wang knows exactly what it got the first time, right? And then that's x1. Whereas Meng doesn't know what Wang got, but it knows exactly what it got the second round. Okay? So this thing and this thing, those are fixed according to what the players know. And to complete the strategy, each player is going, the same answer it wants to give about the round that it knows, it gives exactly the same answer, the same beat for the other round. Okay? So that's the strategy. Why does it achieve value half? Because, well, when do they win? Exactly when x1 equals x2 prime. And this is when they win the first time. This is also when they win the second time. So if they won the first time, they won the second time, and that's it. Okay, so that's the example. Right, so the first round is won with probability half, and the second, if it won, it's won again. It's won with probability 1. Okay, cool. So what happened here? How come the value didn't decrease exponentially, didn't decrease at all? Because, so let's see what happens in this g squared. The probability that the various pair accepts is the probability that they agree on the first round times the probability they agree on the second round, but conditioned on agreeing on the first round. Right? That's probability. And the thing is that while the first round is really, you really play the original game, the second round, you don't play the original game. You play a sub-game of the original game where C1 and C1 prime agree. And sure, you have something given about the probability of agreement in the whole game, but not in sub-games, right? So, right, and the value can be much higher. It can be 1, as we saw. So this is the idea of this work. Let's prevent such things from happening. Let's make sure that the provers can't just like get us stuck in this corner or in the subgame where they can win with probability 1. Let's kind of fortify the subgame. Let's guard the subgames and make sure that they cannot be won with good probability. Okay. Okay. So let me tell you what we do. So we tweak the game such that pair repetition is going to behave approximately like sequential repetition. And there are 2 parts to this proof. The first part is this fortification. It's a very simple operation on those projection games. It maintains the value, somewhat increases other parameters like what's the randomness that the verifier uses and what's the alphabet of the prover, but only in completely allowable ways. And the idea is that we'll take the game, we'll do this fortification where we protect the subgames, and then we repeat it. Okay? And so the second part of this work is to prove a Parallel Repetition Theorem for fortified games. And what we prove is that if the game is fortified for the right parameters, then the value of g to the k is bounded by about the value of g to the k. So let me just tell you how to read those parameters. So fortification has 2 parameters, delta and epsilon, that we are going to discuss in a second. What this thing tells you is that, right, you want this to be the error term, you want this to be small, arbitrarily small. So it means that if you know that you want to do k repetitions, you're going to pick epsilon to be polynomially small in k. So this is going to be negligible, and you really are going to have here the value of g to the k. And the delta should be exponentially small in k that you want to get. And it depends on what's the alphabet of the assignment to the variables, and depends on epsilon, but okay. Good. So these are the 2 parts of the work. Yeah.
Just to clarify, so if the value of the game is initially 1, any fortification will result.
Yeah. 1 keeps being 1, and per repetition maintains 1. Whereas if it's smaller than 1, Fortification doesn't change the value per repetition, decreases it like sequential repetition. Okay. And as I show you exactly what fortification does, and I show you this, like, we'll talk about what happens to the other parameters and so on.
Delta is not pure at all. It's a value of k to the k. You just need delta to be small.
I need delta to be small.
Yeah, it doesn't even appear in the overall
Yeah.
scale, actually.
Yeah, but you need this to be small to be able to argue that. Okay? The parameters of the game. Okay? In ways that we'll discuss in a second. Let me do some advertisement. One thing is that notice that I showed you before this non-interactive agreement game, and so I showed you what happened after 2 rounds. The same thing that happens after 2 rounds, you can do it for k rounds. You can actually achieve in this game the value to the k over 2. Okay? So there are games where the value really decreases, not with k, but with k over 2. But what we show is that if we tweak it, it doesn't do that. Okay? So that's an important point. Like all the previous analysis of per repetition, because they had to work for every game, they really had to lose this over 2, this square root in the value, and we don't have to lose it. So this is one thing, and I call it no round is left behind. Right? So basically, what does this mean? It means that that you make k rounds, but you really just benefit from k over 2 rounds. And here you really benefit from each and every round that you make. Okay? So it's really ideal parameters. And then the other thing is that it's combinatorial, it's elementary, there is nothing like more than that going on. Just the 2 corollaries of this theorem. One thing is, Reed had this in 2005, this combinatorial PCP theorem, and this was very nice, but the error probability was 0.999. It was a basic PCP theorem, and you really want for hardness of approximation, you really want this 0.001. So now you can apply this per repetition, and you get this combinatorial PCP like you need for hardness of approximation. You get it with like a nice proof, and you can get the 3SAT best result, or you can get like all the other hardness of approximation that you want. Right? And yeah. The other implication, so Ran and I had this, we could get a PCP, like this close versus close game, with polylogarithmically small error, but only for some polylogarithm. And if you apply per repetition on it, you can get it to be polylogarithmically small for any polylogarithm, which actually was important because for set cover we needed a specific polylogarithm, which wasn't the polylogarithm we got. And this was also achieved slightly before this work by Irit and David. They also had a different analysis of per repetition. We give slightly better parameters there. Yeah. Okay, so you can apply this to. Okay, yeah. No, but my version gives slightly better parameters. Right, so yeah, so you can get maybe you can get better results slightly, right? No, their version works very well if it's very close to 1. It just so the reduction. K over 2. Oh yeah, they also have a version for value very, very close to 1. Yeah, they have a different version for. You're right. That's very observant. Yeah. Yes. Yeah. Yeah.
I don't want that to happen.
Yeah. Right. So we need to invest fewer rounds in order to get the same probability, which corresponds to a reduction that is slightly more efficient, right? By this square thing. Okay. Fine. But I think, you know, this is good for kind of the idea, for the technique. Right? It's something that you can teach, something that you can explain to anyone. Okay. Okay.
I mean, anyone.
You did say that anyone would understand.
No, I think that this is something that any theoretical computer scientist can understand with yeah, okay. Okay. Good. So, right, as I said, there are two parts. There is a fortification part, and then there is a parallel repetition part. So let's start with the fortification, and then do parallel repetition. Okay. So here it is, right? So we have a game, and we're just trying to simulate the game, but in sort of a robust way, in a fortified way, so the subgames are guarded, right? So that's the intuition. So the verifier has some game that it wants to simulate. It just, you know, picks the variable, picks the two questions that it wanted to send to the provers, just like before. But the difference is that now it picks extra questions, right? So it really wants to answer X. It's going to pick a bunch of other, like W-1 other questions. And so for the first prover, and then W-1 questions to the other prover, put the ones that he actually cares about in the middle somewhere, and he sends all of those questions to the first prover, all of those questions to the second prover. And W has to be of the right size. So the easiest way to think about them is that you just pick the W-1 questions independently at random. And the location independently at random. Okay, so this is just random sets that happen to contain the X and the X prime that you actually care about. Okay, so this is a very useful way to think about it. You really don't have to choose everything independently at random. We don't like choosing things independently at random because it uses a lot of randomness, and it's really much nicer to use linear randomness. So actually, it's enough to pick those using an extractor. So you can imagine, so hopefully Avi did his work well and everyone in the room knows extractors. Not necessarily. So extractor is a bipartite graph that has a property that I'll show in a second, but it's it's a bipartite graph, and you can think of here you have the questions that you actually want to ask, and here you have sets of, right? So kind of think of each one, think of the neighborhood of this vertex, and you just pick, you want to pick this guy, so instead you just pick a random, a uniform. It's a biregular bipartite graph. You just pick some random set that contains it and send the entire set. Okay.
If you think of this X and X prime are picked for the universe of n elements, then if you want W of them, there will be n to the W possibility. What you want to do is to have these are all subsets of size W. What you want to do is to restrict your collection of subsets to be just n squared, let's say. They are just n squared, even though W may be log n. You want just n squared sets, but they are so randomly arranged in the space of all subsets that they look good.
You know, do you know expanders? Yes. That's it. This is all you need to know, right? So think about an expander on the set of all possible questions, and just think of doing a random walk. Choose a random walk that contains the vertex that you actually care about. A constant degree expander, right? And then you don't have to consider all possible choices of questions. You just random walks, okay?
So what would be the degree of the expander? Constant
degree, but you care about the length. The length is this W.
Constant is 4. It's independent of the
Yeah.
types.
but the length of the random walk is not. Okay? Okay, but you know, it's actually, it matters kind of for PCP, or you know, to get a very efficient reduction, that these are correlated rather than independent, but for conceptually, just think of independent extra questions. Okay? Good. So you send, so the verifier sends the whole set of questions to the players, and then the players respond with all of the answers for each and every one of the questions. Okay? And then, in particular, they give an answer for x, and in particular, they give an answer for x prime. And so the verifier just does whatever test it wanted to do on the two answers.
It may not be clear from your description, but x and x prime are in the same coordinate.
No, right? You just care about, you send a set, and you get all of the...
So we don't, or you don't put it in the...
No.
Not necessarily.
No. You just send sets, get answers. In particular, you get the value of the values that you actually care about. Okay? Yeah. Or think about it, you send set, right? So there is no order. Okay? So that's fortification, that's it. Okay. A few remarks about fortification. Those of you who know this Feige-Killian work, the old work that I mentioned, know that this is, it looks very similar to what they had. They called it confuse and compare. But they only consider this W equals 2. So you have the question you actually care about, and you have an extra independent question. Okay, and here it's really important that you have many other questions, and it's not important that it's independent. Okay, so this is one thing. The other thing, this may feel weird because it may feel to you like we're making something that looks like W rounds instead of just one round. It's not really W rounds because you really just have one test. If you take your question and you choose a bunch of like extra questions independently, you don't expect to have more tests than just this one test that you kind of planted.
Yeah.
I call this one test, and the reason I feel good about myself for calling this one test is that those are all correlated with the question that I actually care about. Right? It's not really that I do independent extra tests, both because there are no extra tests other than the one I planted, and because they're not independent. Right? So I use the randomness that I use is about the same randomness as the original game. Okay. The randomness, yes. This is the, yeah. Because the randomness is what people care about. The randomness corresponds to the kind of the blow up in the reduction. And you want the blow up to be small so you get a good relation between the time you need for the approximate problem and the time you need for the exact problem. Okay? I can save on randomness because here I'm not trying to, I'm trying only to maintain the value. I'm just trying to gain an extra property that I'm going to describe to you next. No, oh, why not? Because it doesn't work. Yes. No, it really doesn't.
I guess not.
It doesn't work, right? No, there are actually impossibility results, and actually much stronger impossibility results should be provable. It's really, it doesn't work, right? You would think that instead of doing the k-test completely independently, you can have them correlated. It just does not work. Yes, because I want to achieve property. I'm not trying to do anything with the value when I do fortification. The value remains the same. However, I'm trying to get an extra property. And the extra property is a preparation to my pair repetition. The extra property is going to arrange everything I need for the pair repetition. Okay? So what's a property that I'm trying to get? Basically, I'm trying to make sure that there are no subgames with very high value. That there are no large subgames with very large value. Okay, so to really arrange it, there are no subgames of very large value. One can show that it's basically equivalent to the value is much smaller. So I don't consider all possible subgames. I consider only a family of subgames that I call rectangular. Are called rectangular subgames. And in rectangular subgames, all I do is I limit the set of questions to each of the provers. So there is a whole set of questions that each prover can get, and I only consider subsets. One subset for the first prover, one subset of the other prover, and say a fraction at least delta. This is the delta parameter in the fortification. And the verifier, it picks like variable and two clauses, but the clauses have to come, I condition on them coming from the sets that I fix. This is a subgame. A subgame is defined by the two sets. Okay? Is the definition of rectangular subgames clear? Anyone wants to ask me a question? So what I can show, this is like the first lemma, like the first part of this work, is that if I do this transformation that I showed you before, then for any rectangular subgame where the fraction is at least delta, the value is at most the original value plus epsilon.
So rectangular subgame, you mean that you take these rectangles, you take a range of
Yeah. Mm-hmm.
completely uniform range.
Yeah. Yeah, exactly. Okay, so these are the delta epsilon in the fortification. This is like the first part of the work to show that the transformation gives this property. Okay, that rectangular subgames behave well. The value doesn't change much. And this follows basically directly from the property of extractors. Let's not do it now, so I can. Yeah. Yeah. Exactly. Right. Yeah. So what I'll show here to prove this is that I actually really simulate the original game when I consider a subgame. Because the subgame is, in this larger world of subsets, the planted thing is still uniform in the original game, and the value that you can achieve is only the value of G. Okay. Yeah, we're not going to do that. Let me make a few remarks. One thing, right, some of you may know that parallel repetition on extractors is a special case that was analyzed before by Ran and others. And then, one might wonder why this wasn't done before. The issue is that the fact that the graph is an extractor doesn't mean that the game is fortified. This is a special property of this fortification, of the specific way in which we use the extractor to get this fortification. Okay, so previous works that worked on extractors couldn't use this extra property. People do it on expanders, people did it on extractors, but they just didn't have this property. This is the first thing. Let me just mention one more thing. It will look to you like maybe it's a weird thing it's an unnatural thing to have this extra property. Actually, natural games on extractors are fortified by nature. Okay. Second thing, you can get worried because what we did here in fortification, we increased the randomness of the verifier before we repeated. And then the repetition increases the randomness. So, was this bad? This wasn't bad because we gained enough in the better parameters for the repetition to compensate for the fact that we slightly increased the randomness before we repeated. Right, the size is like 2 to the randomness. This is the definition. Second, another thing that can bother you is that now I ask the provers to give W times more answers than before, right? We increase the alphabet. But the thing is that it's not so bad because in repetition, we increase the alphabet anyway. And the thing is that we gain kind of the value that we want to gain from the repetition. So this is completely legit. What? So you have some blow up, yeah. So you don't have the exact right trade-off between the alphabet and the arrow. but it's just a difference of a constant, and it's a constant in the exponent. Yeah. This is Avi's constant in the exponents of constants. Yeah. And yes, and the nice thing is that we preserve this structure of constraint versus constraint, or the projection structure. We don't preserve unique games. If we start with a unique game, we don't get a unique game. Okay. Good. So this is what I wanted to say about fortification. Let me show you the proof of parallel repetition. Can I go for like 5-10 more minutes? Yeah. Okay. So this slide has the entire proof of parallel repetition. It's a very simple proof. The reason I can show a simpler proof than what I do in the paper is in the paper I consider k repetitions. And here I want to show you just how you do squaring. Okay, so k equals 2. And the thing is that note that while if I can do squaring, then you should be happy because I can square and square and square, right? Okay. So what do I want to show? I have a game which is delta epsilon fortified, either because I applied the transformation that I had before, or because the game happened to be fortified ahead of time, like just naturally is fortified, which actually happens. And now I want to bound the value of g squared. Okay, so this is this thing. And assuming that delta is sufficiently small, and the sufficiently small that I need here is written here. Sigma is the alphabet of the variables. Okay. So I want to show that the value of g squared, right? So we start with value g, and now I want to show that it's about value of g squared. And what I'll show is that it's at most the value of g times the value of g plus epsilon. And if I do that, we're happy. Okay. Good. So let's do that. So assume when we have contradiction that I don't have parallel repetition. So what does it mean? It means that there is a strategy for the players in this repeated game, g squared, that does better than what I wrote here. Okay, good. So let's do just conditioning, right? What's the probability of agreeing, of winning g squared? It's the probability of winning the first round times the probability of winning the second round, condition on winning the first round. So I'm going to think about it as my variable, I call it the y's, and my questions, my constraints, I call them the x's. Okay. So I know that the first round, I just played the original game. And all I care about is really the second term in my product, which is the probability of agreeing on the second variable conditioned on agreeing on the first variable. And
They get no information from the question.
I don't assume anything.
No, but you say that in theory the first one is the second one.
No. When you say this conditional probability formula just says what's the value the first term, it's just what's the value of succeeding in the first coordinate.
Yeah, but this is the first coordinate you play without any further.
No, it doesn't.
No.
On
No,
one
the
coordinate you
first
can.
coordinate is like the original game.
Yeah,
It
it is
is-
like the original.
Yeah, it's distributed
You
exactly.
get no information from the question.
The whole problem is
No.
that you want to be correct on all the questions.
Yeah.
It's obvious that for any particular question you cannot succeed more than the value of the game.
It's just this.
Because you get no information.
No.
It's not because the projection of the distribution of questions
It's exactly the original
questions are
game.
independent per coordinate. You cannot on any particular coordinate you cannot succeed. By definition, it's a strategy. Yeah.
Okay. So really, the meaning of parallel repetition doesn't work is that in the second round, we managed to succeed with probability larger than value of g plus epsilon, conditioned on succeeding in the first round. This is exactly this. And I want to show that this leads to a contradiction. Okay. So here is what I do. Let's consider what happens in the first round. So the questions say are x1 to the first prover, x1 prime to the second prover, y1 is the variable that we chose. Let's consider some specific value to the first variable. So sigma is some label over the large alphabet. And let's define, I want to define a rectangular subgame, right? Because I wanted to use my fortification. So I'm going to define the set S. And the set S is consider all of the x2s that if I already fixed, I'm fixing what happens in the first coordinate. I'm fixing all the questions to the first coordinate, and I'm fixing the answer to y1 of the first round. Let's take S to be all of the second questions that are consistent with my fixing. Okay, so the strategy gives values to y1 and y2 for every pair. And now I want to consider only the pairs that agree with whatever I fixed here. So this is for the first prover, and I'm doing the exact same thing for the second prover. Okay. And notice that I really defined here some rectangular subgame, because I just limit the set of possible questions to the first prover, and I limit the set of possible questions to the second prover. And yes. So now I have two cases. Either the rectangle is big enough or the rectangle is not big enough. Okay. If the rectangle is big enough, then I can use my fortification condition and say that restricted to this subgame, the value is at most the value of g plus epsilon. Right? So this just follows. What happens with small rectangles? Well, what's small rectangles? Small rectangles are exactly, small is like what's the probability of them being chosen, right? So small rectangles just don't contribute much, right? So I do a union bound over all choices of labels to the variable, and that's it. I just, I bound all the contribution from all of the possible rectangles, and that's it. I think that you're fine because you do a partition, but even 2 epsilon, yeah, on me. Yeah, that's it, right? Simple. This thing? It follows directly from the definition of extractor, directly.
So if you want to continue squaring,
you have to fortify every time. You can, according to this, you'll fortify every time. You actually don't have to fortify all the time. What I do in the paper is I fortify once, and I show that you can actually get k times out of it, k repetitions out of it. But it's just like a slightly more complicated proof that, why. But I'm happy because the size of the alphabet is always in correspondence to the value that I get from repetition. So.
But you change the data, so when you square for the next time the data will be smaller.
Yes. Yeah. But it's always in the right, it corresponds in the right way to the other parameters, so I'm happy with that. That's it. I want to end with this slide. And this slide is about how pair repetition is really everywhere. So I got interested in that because of this application to hardness of approximation. This is like the basis of all hardness of approximation. It really came out of like cryptography and zero knowledge protocols. The applications to quantum computing, because they really care about two-prover games. Two-prover games is like their Bell's inequality that proves that, proves Einstein wrong about that quantum mechanics is not right. And this amplifies that. So many connections to communication complexity, like some theorems and compression, disjointness, the disjointness low bound, which is by itself extremely important for other things, is actually the proof is almost the same as pair repetition. It has ties to geometry and so on. The thing, I think that the main take-home message of this work is that pair repetition is easy. At least for many natural games, or it's easy if you can slightly tweak the game. And right, I don't think that it should stop with what I showed you. I think that there are many many other applications once you realize that it's so simple. That, you know, this tensor product kind of structure is not just in two-prover games, it's also in combinatorics, right? You have Shannon capacity, you have all kinds of things. I think that those ideas are useful. Have some follow-up works that use those ideas. I think that it should be much more useful. Yeah, that's it. Well, it depends. The thing is, this is interesting even without randomness, right? If you just do everything independently at random, this is super interesting, and right, then this is like, I think, the simplest.
No, but the answer to your question is no.
What?
Randomness is not the only.
Why is it for hardness of approximation? Yeah, so I can explain that, right? So, oh man. Right, in the end, what do you want to get? You want to get this reduction from FreeSat to this like approximation problem, whatever this is. And what happens is that your reduction, you're going to write down the strategies of the provers, right? The reduction, the variables of the reduction are really write down the strategies of the two provers, and so to write down is like for every possible question of the provers. So every randomness, so the size is going to be 2 to the randomness, okay? So this is the size of this reduction. And the size of this reduction is immediately, right? So if you started with here something of size n, so if you do a reduction which is n to the 100, then if all you know is that here you have a lower bound of 2 to the omega n, then here you know that there is a lower bound of 2 to the n to the 1 over omega. Because the n now is a different n, right? So you get a much weaker lower bound here if your reduction is wasteful. So we want this reduction to be as little wasteful as possible. Okay. More questions?
Is it possible that one can get PCP with soundness 1 to point out directly by something?
Directly from what?
From
So, yeah, no, so the thing is, we don't, per repetition, if you want to do, like, to get from, like, to get to error, which is 2 to the minus k, we think that you really need to do k-independent tests, which means that if you started with size n, you're going to get to size n to the k. So if you want this to be subconstant, this is going to be super polynomial. It doesn't work.
Well,
We don't know.
It may work. We just don't know how to make it work.
No, it's an extremely
This is
difficult.
called, the sliding scale conjecture.
Well, the sliding scale conjecture
It's
says.
specific, yeah, it's
The sliding scale conjecture just says that you can get error 2 to the minus k with low size somehow. We have ways,
conjecture that can be done.
but not necessarily through per repetition. No, but still you need, so you can get, this is log, so you'll get log here.